I'm Shiho Asai from Organic Standards Group, National Meteorology Institute of Japan, NMIJ. Thank you very much for giving me this opportunity. Today, I'm going to talk about determination of long-lived radionuclides by ICP-MS for radioactive waste disposal in Japan. In Japan, high-level radioactive waste is planned to be disposed of in a deep geological repository. To evaluate the long-term risks associated with radiation exposure, estimating the inventory of long-lived radionuclides such as selenium-79, zirconium-93, palladium-107, tin-126, cesium-135, and neptunium-233 is essential. Since there have been few available measured data in Japan so far, theoretical predictions based on existing nuclear data are employed instead of measured data. So we have been committed to measuring long-lived radionuclides in real waste samples from Japanese commercial nuclear power stations for verifying the theoretical values. These are the long-lived radionuclides we measured by ICP-MS. All the nuclides have long half-life, more than 100,000 years. As is well known, activity can be calculated by this equation. This equation suggests that a nuclide with longer half-life has a larger number of atoms. For example, cesium-137, which has a relatively short half-life of 30 years, can be easily detected by gamma detector, but a long-lived pure beta-emitting nuclide, cesium-135, cannot be observed. In contrast, mass spectrometry enables cesium-135 counting as well as the other cesium isotopes. This graph shows mass spectra of fission-genic nuclides. You can see fission products and trans-uranium elements at one time. Even stable nuclides can be observed, which is not achievable in radiation measurement. Thus, we can draw out various information from the shape of mass spectra. We always measure full spectra by ICP-MS as a first step to get a rough information of chemical and isotope compositions. As I mentioned earlier, we measured long-lived radionuclides to verify nuclear data used for inventory estimation of radioactive waste. Here, a well-characterized spent nuclear fuel used in Japanese commercial PWR with a detailed radiation history was used as a sample. A UO2 pellet taken out from the fuel rod was dissolved inside the hot cell and diluted to adjust the concentration below the regulation level. Target nuclides were chemically purified and then introduced into the ICP-MS. From here, I'm going to focus on the measurement of cesium isotopes as a representative of long-lived radionuclides measured by ICP-MS. Cesium has a major 4 isotopes, 133, 134, 135, and 137. Among them, the amount of cesium-135 generated by nuclear fission is not well investigated due to the lack of measured data. Thus, we try to verify the theoretically predicted amount of cesium-135 in a spent nuclear fuel samples by measuring it by ICP-MS. As you can see, All the predicted values for cesium isotopes agreed well with those measured by ICP-MS. The results demonstrate the validity of applying the existing nuclear data to estimating the inventory of potential radioactive waste disposal sites. Regarding the cesium-135 determination, the calibration curve method can be the first option. As shown in this graph, 133, 135, and 137 can usually be found when you introduce the cesium-135 containing sample to ICP-MS. Thus, the concentration of cesium-135 is an unknown sample. In an unknown sample can be calculated by using the calibration curve of cesium-133 and the measured 135-133 ratio. Here, you can employ cesium elemental standard solution with a certified mass fraction of cesium or cesium-133 as a calibration standard. In ICP-MS, the measured signal ratios are not the same as the ratios of their number of elements. This is generally called mass bias or mass discrimination. As you may know, almost all types of ICP-MS are inevitably subjected to this kind of fractionation. In general, for 135-133 ratio, around 3% can be deviated from the reference value depending on the instrumental conditions. If you measure a standard solution, including 135 along with 133 and 137, the relationship between the mass differences and the ratios of the reference ratios to the measured ratio can be established, which provides mass bias correction factor. The mass bias correction factor obtained through the fitting is applicable to the determination of cesium-135 content in unknown samples. However, there is no commercially available isotope standard applicable to mass bias correction for cesium-135 quantification. Furthermore, methods for uncertainty evaluation has not been established yet. So we started to develop cesium-135 standard solution to achieve a simpler mass bias correction. We selected the JCSS cesium-137 standard solution as a candidate cesium-135 standard solution. Here, JCSS is the calibration service system that assures the traceability to national measurement standards in Japan. As you may know, cesium-135 is generated by nuclear fission along with cesium-133 and 133. Therefore, we expected that the cesium-137 standard solution include comparable level of cesium-135. The features of this cesium-137 standard solution is that it does not include additional cesium-133 as the cesium carrier. Usually, commercially available cesium-137 standard solution contains a high concentration of natural cesium, which is not appropriate for cesium-135 quantification by ICP-MS because it leads to significantly low ratio of cesium-135 cesium-133. This relationship can be calculated using the mass fraction of cesium-133 obtained through ICP-MS and the radioactive concentration of cesium-133 obtained through both ICP-MS and gamma detection. Now, we are checking the stability and homogeneity in accordance with ISO Guide 35. There are the publications relevant to determination of long-lived radionuclides by ICP-MS. Most of the above works were done in the facility in Japan Atomic Energy Agency. I'd be grateful if you get interested in our work. This is all my presentation. Thank you very much.